Hi everyone, today I want to tell you about the history of the salicylic acid. So, to begin with, salicylic acid is organically found in the bark of a willow tree that comes from the genus Salix. So, that's the reason why this compound names salicylic acid. So, at the early history, these compounds are recorded to reduce pain and the fever. So, at the 19th century, this compound was shifted from the herbal decoctions to the extraction of a pure active compounds that been used for the modern pharmacology. So now, let's move to the next part, which is we need to know about the chemical identity and the official nomenclature. So, the first thing first, based on the diagram, we need to know the IUPAC name, common name, and the molecular formula for this compound. So, the IUPAC name for this compound is 2-hydroxybenzoic acid. It is because it is come from the carboxylic acid group. So, the common name for this compound is salicylic acid, while the molecular formula is C7HCO3. So, let's move to the next slide. So, this molecule are unique because it has two different functional groups on a single benzene ring. So let's see. First thing first, we have benzene ring, as I said. So what is the benzene ring? Benzene ring is an aromatic ring that stabilizes the molecule through the resonance structure. And the second one, we have hydroxyl group OH that are capable for the phenolic esterification reactions. And the last one, we have carboxyl group COOH that are contribute for the acidic properties and carboxylic acid reactivity. So next, we need to know about the physical and the chemical properties for this compound. First thing first, this salicylic acid will become solid at the room temperature and appear in a white crystalline powder. Next, it will melt at a point 158 degrees and it can be reached the boiling point up to 211 degrees. And it is also, the salicylic acid is a very low solubility in the cold water, but it is well in the ethanol and the boiling water.
Salicylic acid has many important biological applications, especially in medicine and dermatology. In pharmacology, it serves as the precursor for aspirin, one of the most widely used drugs for pain relief, fever reduction, and inflammation control. In dermatology, salicylic acid is commonly used in skincare products because it acts as a keratolytic agent. This means it helps remove dead skin cells, unclog pores, and reduce acne formation. It is also used in treatments for dandruff, psoriasis, and warts due to its exfoliating properties. These applications demonstrate how a naturally occurring compound can provide significant benefits in healthcare and personal care industries. Besides its medical uses, salicylic acid also plays an important role in agriculture and industry. In plants, salicylic acid functions as a signaling molecule that activates defense mechanisms against pathogens and environmental stress. This helps plants improve their resistance to disease and adverse conditions. In industrial applications, salicylic acid is used as an intermediate in the production of pharmaceuticals, preservatives, dyes, fragrance, and cosmetic products. Therefore, salicylic acid contributes not only to human health but also to agricultural productivity and various manufacturing processes. One of the most important chemical reactions involving salicylic acid is esterification to produce aspirin, also known as acetylsalicylic acid. In this reaction, the hydroxyl group of salicylic acid reacts with acetic anhydride in the presence of an acid catalyst such as sulfuric acid. The reaction introduces an acetyl group into the molecule, producing aspirin and acetic acid as a byproduct. This synthesis is widely performed in chemistry laboratories because it demonstrates how functional groups can be modified to create compounds with different pharmaceutical properties. The production of aspirin is a classic example of how organic chemistry transforms natural compounds into valuable medicines.
Now, let's delve into our second mechanism, synthesizing wintergreen oil. The core focus of this mechanism is an acid-catalyzed esterification, more widely known as the Fischer esterification. Unlike the previous aspirin synthesis, This reaction takes place at the carboxyl groups of the salicylic acid. When we react salicylic acid with methanol in the presence of concentrated sulfuric acid as a catalyst, the carboxyl group's terminal is modified into an ester group. As a result, we obtain methyl salicylate or wintergreen oil, a sweet-smelling aromatic liquid, along with water as a byproduct. Moving on, let's take a look at why the salicylic acid molecule is so unique. We can fondly call it the chemical chameleon due to its bifunctional molecular nature. This incredible flexibility stems from the ability of salicylic acid to undergo independent reactions at two different terminals or functional groups. First, if we modify the hydroxyl group's terminal, we can synthesize aspirin, which acts as an analgesic agent. Second, if we instead modify the carboxyl group's terminal, we obtain methyl salicylate, the main component in liniments and fragrance. What is most fascinating is that if both groups are left completely unmodified, salicylic acid itself naturally acts as an keratolytic agent for skincare. Pretty remarkable, is it? To wrap things up, looking back at the journey of salicylic acid, it's amazing to see how it evolved from a simple traditional remedy found in willow bark into an absolute necessity in modern organic chemistry laboratories. What makes this molecule truly special is the perfect balance between its hydroxyl and carboxyl groups. This dual nature is exactly what gives it such powerful medicinal benefits, while also making it highly versatile for industrial use.